Welcome to the first in a two-part tutorial on the topic of vectors. Now, vectors, when you first see them, are odd. They are unlike really anything that you'll have seen before in maths, and you might get a reaction of, these are clumsy or hard to understand. But please believe me when I say that vectors are so helpful and so powerful, and they're really one of these mathematical tools that comes along which makes everyone else's life much easier. So if you are an architect or a scientist or someone who works in sort of computer science or statistics, you will be dealing with vectors, and they will be making your life 100 times easier than otherwise. And I can attest to that as a physicist, that really the much of the language of physics is in terms of vectors, because they're so natural in describing things in a spatial environment. So that's just a little bit of a motivator there, that even if this might seem like an odd topic when you first see it, be assured that this is really something that's very powerful. You might not quite see the power of it unless you study it a little bit more, perhaps for another couple of years after this level of maths. But still, nice to know about, even if your maths career ends at this level. So what is a vector? Well, simply put, for us, it is a quantity with both magnitude and direction. Okay, we can just sort of think of that as a definition, and actually we can represent it therefore very beautifully in 2D by an arrow. On the page, this is a vector. I'm going to call it A, that's my vector. And when we write vectors, when you see them written in kind of books or exam papers, they're often written in kind of bold font, because we can't really do bold font when we're writing with a pen. One common notation is just to put a line under it. So that is a vector A, and it's defined by its magnitude. It's just its length. Okay, so the length of that line is the magnitude of the vector, and the direction is just the angle it's pointing. So this vector is pointing in that direction, and the vector is not defined by where it is. So drawing exactly the same line, same length, same direction, that's just A again. That's not a different vector. Okay. So what can we do with vectors? In this first tutorial, I want to talk about a couple of things. One is sort of arithmetic with vectors, and the second is just staying in 2 dimensions. I want to talk about how we can represent vectors using something called components, which is very powerful and sort of natural, which I think will help you manipulate vectors. So first of all then, just thinking about arithmetic, let me see what happens if I multiply a vector by a number. So what would we mean by twice a, for example? Well, when we multiply a vector by a number, what we mean by that is that the magnitude of the vector is essentially multiplied by that number, but the direction is the same. So this vector I drew here, A to A, would be the same direction but twice the length. So that would be the vector 2A. And likewise, I can imagine a vector which was in the same direction as A, but half the length. We would represent that as 1/2 of A. So multiplying a vector by a number just doesn't change the direction, but just changes the magnitude. You might ask, what about multiplying a vector by -1? What does -A look like? It's the same length vector, but pointing in the opposite direction. Okay, so a vector half the length in that direction would be -1/2 A. So that's multiplying vectors by numbers, both positive and negative. What about adding vectors together? Well, for example, this vector 2a I could think of as a plus a. So a plus a equals 2a, and namely that vector plus itself, I put the second vector, the tail of it on the head of the first, gives me, sorry, it's a rather bad drawing there, gives me that vector 2a. So there's literally a plus a. I can just introduce another vector. Let me call this vector b. There's b. And I can think about a plus b. So here's a, becoming quite a familiar friend now, a. And adding b, I just put the tail of b onto the head of a. And if we go from the tail of a to the head of b, we define that to be a plus b. So you can just add vectors together in this very natural way, and then this would be a plus b. And likewise, I could take a and I could add to it the vector negative b. So negative b would be the vector with the same length but opposite direction. So there's the vector negative b. Okay, here's the vector a. And so going from the tail of a to the head, as it were, of negative b, this gives us the net vector a take away b. In other words, a plus the vector negative b. So you can add vectors and you can subtract vectors like this. Okay. Now you might ask, oh, okay, so that's multiplying by number and that's adding. How about multiplying vectors? Well, that's a really interesting topic. It is outside the curriculum at this level of maths, in fact. Just to say that there are different definitions, different ways of multiplying vectors. You can multiply two vectors and get back a number. You can multiply vectors and get back a vector. Or you can multiply vectors and get back something called a tensor. And all of those things are very, very useful in science, but those are the topic of higher levels of maths, and we won't be covering those in today's tutorial. So let's talk about components now, which is a kind of a way to start to get our hands on these vectors, because so far I've really just been drawing pictures, but we would like to maybe get a little bit more quantitative with these vectors and how we describe them. And if you'll just bear with me, and I do need your patience here, I just want to draw a very quick grid. And so I do apologize because it's not the most brilliant use of your time, but you might find it relaxing. You can either go and get a quick cup of tea or fast forward the video, or just watch me make maybe somewhat of a hash of this. Let's see. I think I remarked in an earlier tutorial that sometimes it's quite relaxing watching people drawing things on YouTube, because they're sort of doing all the hard work and you can just kind of zone out slightly. Actually, that's not too bad at all. Okay, give myself a B for that. That's a little grid there. Let's say that this is the X direction, and let's say this is the Y direction. Okay. And let's use a different color pen. That'd be really helpful. Let's try and draw our friend A on this. Let's imagine that A looks something like this on this grid. Okay, that's kind of pretty similar, isn't it? Similar length and direction. So there's A, our friend A. Okay, and while we're at it, let's draw B as well. Looks something like that. Okay, and let's say that this grid is just in units of 1. So I'm not going to put numbers on, but let's, this is 1, 2, 3, 4 units and so on. So what we notice is that this vector A can be very neatly described as going 1, 2, 3, 4 units in the x direction and 1, 2 units in the y direction. And wouldn't it be nice and simple if we could just represent A using those numbers? And indeed we can, and here's how we write that. We write A equals, and we draw brackets, and we write the x increment on the top, which is 4 units, and the y increment on the bottom. So 4, 2 means go 4 along in the x and go 2 up in the y. Similarly, our vector B here would be 2 units in the x, and it would be negative 2 units in the y direction. Okay, so if I imagine that I add A plus B, so here's A and then I add B to it, I get this vector here, A plus B. We can see that by using the components we can write the following: A plus B equals the vector 4, 2 plus the vector 2, negative 2, and this equals, and all we do now is we add the x components together, so 4 and 2 is 6, and we add the y components together, 2 plus negative 2 is 0. And so this vector A plus B is 6, 0, and we can check that with our figure here. We see that we have a sum which is just flat, so no change in the y direction, and 1, 2, 3, 4, 5, 6 units in the x direction. Similarly, we could look at a vector, let's see, we could have a vector half times A. There's the vector half A. Multiplying a vector by a number, we literally take each component and multiply it by that number. So the vector 4, 2 multiplied by a half, we multiply the first component by a half, so 4 times a half is 2, and we multiply the y component by a half, 2 times a half is 1. And that gives us the vector which we can see tallies with that one. So these components are quite handy. Let's just do one more quick example. Let's say we did A minus B. So here's A. We go 4 units, and then we go 2. So there's A. And let's say we're going to take B away from it. So B is 2, negative 2. So the vector minus B, we would be multiplying B by minus 1, and so 2 times minus 1 is minus 2, negative 2 times minus 1 is plus 2, so the vector negative B is negative 2, 2, as we would expect. So there's the vector negative B, and adding negative B to A gives us this vector here, and we can just work that out. A take away B is the vector A, 4, 2. Let's actually add the vector negative B. We could equally just say minus 2, negative 2, but let me just add the vector negative B here. Completely equivalent. And then we just add the components here. So 4 plus negative 2 is 2. And 2 plus 2 is 4. And again, that is indeed A minus B. We see we go 2 in the x and 4 in the y. So these components are really very, very useful way to write vectors. I'm just going to cover one more thing in this tutorial, which is an alternative way to write components. And then in the next tutorial, we're going to carry straight on with the technique of using components to determine the magnitude of a vector. But let me just introduce to you this very nice way of writing components. Let's define a unit vector to be a vector that has magnitude 1. Magnitude equals to 1. And then it's very convenient to define a unit vector that just points 1 unit in the x direction. And it's very convenient to define a vector that just points 1 unit in the y direction. And the convention is that we call the little unit vector in the x direction I, and the little unit vector in the y direction j. So we would define then I as 1 in the x direction, 0 in the y, and we would define j as 0 in the x and 1 in the y. And then you have a very nice way of representing vectors, alternative to this column sort of representation. We could write A as 4 lots of I plus 2 lots of j. And we could represent, say, B as 2 lots of I take away 2 lots of j. And then I think this is a nice representation, because you then see very clearly when you're adding vectors, we're adding 4 lots of I plus 2 lots of j, and you can think of I and j as sort of apples and oranges. They don't add, you have to add apples and apples and oranges and oranges. So A plus B here would be 4I plus 2j, which is A, plus 2I take away 2j. So the apples then, 4 lots of I plus 2 lots of I is 6 lots of I, and then the oranges, 2 lots of j take away 2 lots of j is 0 lots of j. We would just write that as 6I. So this I and j notation is actually very, very handy, and perhaps for many applications preferable to using this column representation, but in the end of the day they're completely equivalent. So I hope this has been a helpful sort of first look at vectors. We've sort of defined them, we've talked about multiplying vectors by numbers, we've talked about adding and subtracting vectors, we've talked about representing vectors using components, and how it's very easy to see how the adding and subtracting and multiplying by numbers works with the components. And finally, I've just given you a slightly different, very useful representation of components using these so-called unit vectors I and j, and how you would write A and B in terms of I and j and do arithmetic and so on. So I do hope that is helpful and not too quick. Next tutorial on vectors, I'm going to look at calculating the magnitude of a vector. I'm going to talk about position vectors, and finally I will talk briefly about generalizing this to 3 dimensions, writing vectors in 3D and calculating their magnitude, which you'll see is a very simple generalization of 2D. So hope that's helpful, and see you next time.